लेकिन कैमरा भी तो नहीं आ रहा है सर।
अलाउ नहीं किया होगा, तो कैमरा उसने अलाउ नहीं किया होगा, इसमें कैमरा अलाउ नहीं किया होगा, कैमरा और माइक।
Chandni, can you hear me?
Yes, ma'am, I can hear you.
Hello, Chandni.
हाँ प्रताप.
Okay, fine.
हाँ, वो ब्लॉक किया हुआ था ना, इसलिए वो एक्सेस बंद। हाँ सर, यहाँ जैसे आप क्या बताएंगे ना,
ठीक है.
Hello, Pathak madam, can you able to hear me properly? Hello?
Yes, sir, I can hear you.
Okay. Try to turn on my camera.
Yes, sir, you can.
Am I visible now?
Yes, you are visible.
Am I visible, madam?
Yes, sir, you are visible.
मुझे पता है कि बार बार ठीक करना मुश्किल है। स्टार्ट करते हैं, स्टार्ट कर रहा है।
Good afternoon, everyone. Welcome to today's webinar. So, as everything starts with God's name, we would like to start our webinar with that too. अभयदा जाड्यान्धकारापहा हस्ते स्फाटिकमालिका विदधतिम् पद्मासने संस्थिता वन्दे तां परमेश्वरीं भगवतीम् बुद्धिप्रदां शारदाम् Now I would like to play message from our Honorable Principal Sir, Professor A.K. Sharma.
Good afternoon to all. My warm welcome to the expert of today's webinar, Dr. Nagpur Rao and all participants. It is a matter of pride that the Department of Applied Chemistry, Technology College Jabalpur is organizing a one-day institutional seminar on instrumental method of chemical analysis and its application. With financial support from chemistry. I congratulate Head of the Department of Applied Chemistry, Dr. S.K. Srivastava, Convener Dr. Vasudha Saxena, Coordinator Dr. Chalti Patha, the entire organizing team, and wish them good luck. Please enjoy the webinar. I think it's very good for all the participants and everybody.
Now I would ask our Honorable Head of the Department, Professor S.K. Srivastava, to please welcome everyone.
Okay, Chandni. Respected Principal Dr. A.K. Sharma, TQ Coordinator Dr. Rajiv Chandak, experts of today's webinar Dr. Nagbhushan Rao and all the participants. It gives me great pleasure to extend a warm welcome to all of you participating in this one-day national webinar on instrumental methods of chemical analysis and its application. Dr. Nagbhushan Rao will share his expertise on instrumental methods. I am sure that you will feel enriched with knowledge on different instrumental methods after the completion of this event. I welcome you all once again to this national webinar. Now I request Dr. Chandni Patel for further proceedings. Thank you.
Thank you, sir. Now I would like our convener of this webinar, Dr. Vasudha Saxena, to please welcome our today's speaker. Thank you, ma'am. Thank you, Chandni.
Good afternoon, everyone. A warm welcome on behalf of Department of Applied Chemistry conducting one-day webinar on instrumental methods of chemical analysis and its applications. So to get an insight into this topic, please join me in welcoming our today's speaker, Dr. Nagbhushan Rao Gudeku. He was a former scientific assistant in Quality Assurance Establishment, Director General of Quality Assurance, Khamaria, Jabalpur, from 2007 to 2016. He is a chemist, grade A, in Modern Mineral Processing Laboratory and Pilot Plant, Indian Bureau of Mines, Nagpur, Maharashtra. Please welcome Dr. N. Gudeku. Now, I'm handing over this meeting to our expert. Thank you, sir.
Good morning, everybody. This is good morning, everybody, and it's thank you for inviting me for this expert talk on instrumental methods of chemical analysis and its application. I'm immense thankful to my guide and professor, the S.K. Srivastava sir, who has patted my back and given a great, what do you call it, forwarding for me, and great achievement have been established in his period. I was previously working in Jabalpur in military explosives, and currently I'm working in Indian Bureau of Mines. I'm very happy to share this technical expertise or technical knowledge with the people, and it's my pleasure to be here. Thank you. Now I'll be sharing my screen. Hello.
Yes, sir, you can start presenting.
Okay. On today's lecture, on today's discussion, we will be discussing about the instrumental methods of chemical analysis and its application. Today, we will be focusing on certain instrumental techniques which are used in chemical analysis of ores, minerals, and certain environmental samples. Today, we will be seeing the instrumental techniques regarding certain XRF techniques and spectrophotometric methods, atomic absorption spectroscopy, and so on, and its application, how we apply to the real field testing of chemical analysis. So, first coming to the analytical chemistry tools to be a cutting-edge technology in the field of chemistry used in problem solving in various disciplines and application by utilizing certain physical and chemical properties of the matter. We are just utilizing our chemical and physical properties. This is the fundamentals in which, by utilizing certain physical properties or chemical properties, we are getting into some instrumental techniques. Now, the application of these instrumental techniques are given in a wide range of disciplines, where you can say it is applied to environmental, geology, medicine, astrophysics, engineering, toxicology, material sciences and metallurgy, agriculture, and biology. You might be wondering what you very well know about environmental, how the analytical techniques are suitable for environmental techniques, just like SOx, NOx gases, or in an atmosphere, or some water pollutions, analyzing the water pollutions, and somewhat in soil contaminations also. So the environment consisting of air, water, and soils. So we will be focusing on the environmental aspects of this analytical techniques. This coming to geology, this is a very important aspect of analytical chemistry, where the field is applied for the analysis of ores, minerals, etc. And some other, for example, you might be wondering why these analytical chemists are very most important in wide varieties of these branches. For example, medicine. You may be knowing the drug analysis. The drug analysis and some other pharmaceutical industries, this is also applicable. Now, coming to astrophysics and physics, right? Meteoroids, and use one of the meteoroids or some of the particles which are coming from the universe into the atmosphere can be coming under this segment. And engineering is also a wide variety in civil engineering, analysis of materials, metallurgical engineering, and petroleum engineering. There are so much of a wide scope of these analytical applications. So an analytical chemist plays very important role in analyzing all fields, and he has a very specialized subject and utilizing his physical and chemical properties of particular materials. Now coming to toxicology. Toxicology is in a forensic sciences. The applications are also widely used. In toxicology, for example, in a sports academy, somebody has been found broke with certain drugs. The sports authority will be interested in analyzing the blood samples or the urine samples. There, the analytical chemistry it plays an important role. There, the drug authority is nowhere coming into the field and is not at all interested in what are the methods that are present in these applications. So, in toxicology, the analytical chemist plays an important role. Now, coming to material science and metallurgy, as I already said, that in modifying certain materials and some high energy materials like explosives and some metallurgical applications like modifying the strength of the alloys, etc. Percentage composition is very important for analyzing for this analytical techniques. So in agriculture, for general pesticides and water, general pesticides and fertilizers can be coming under this agricultural discipline. And moreover in biology, in estimation of urine samples, the estimation of fluids, iron content in blood, or the what you call as potassium and sodium content in some of the body fluids. This all comes under the biology, where the analytical applications are quite suitable. Now, I mean to say that an analytical chemist plays very important role in analyzing various fundamental branches of sciences where the application is suitable. I mean to say that, for example, an astrophysicist or a geologist or a biologist or a material science person, he may be knowing the knowledge of what composition is required and what composition could be manipulated or what composition could be adjusted in order to give a particular output of the product. But an analytical chemist can really suggest how much composition is there in that particular materials or particular products. Now, coming to the analysis, you very well know about the techniques of the analysis. It's quite simple. It's a qualitative chemical analysis and quantitative chemical analysis. This is the qualitative chemical analysis is generally and a quantitative chemical analysis. Just a minute. So these are the both are very important in the estimation of any analysis. It is generally the qualitative methods are applicable for the identification of the materials. So the stoichiometric ratios or the exact species that are present in a qualitative methods can be estimated. I mean to say the quality that what is the radicals or what are the cations or what are the anions that are present in the particular sample can be analyzed by this qualitative chemical analysis. Now coming to quantity, you are estimating the proportion, giving the idea about the relative amount of species that is present in the substance. It is under analyte. You need to analyze the analyte, and therefore it needs to be quantified, the percentage that is present in a material. The analytical chemistry is a branch of liquid sciences.
Nayan Puria, please stop your video and audio.
Hello. Am I audible? Hello? Is there anybody? Audible? Am I audible? Hello?
Sir, you are audible, but somebody is presenting screen.
Okay, thank you. Now currently we are coming to the analytical.
We are unable to see your slides.
branches of
Whoever is presenting,
I am able to see you people.
Nayan Guria.
Thank you. Now coming to the wet chemical analysis, basically this is containing of the two gravimetric analysis and volumetric analysis. Because gravimetric analysis are the only techniques.
Nayan Puria, please.
For example, carbon sulfates and certain leads,
This one only presented.
P and silver. This is silver actually. Can be analyzed by this gravimetric analysis. Now coming to volumetric analysis, it is the estimation of the quantity of the material by volumes. This is mass measurements. Gravimetric measurements are by mass measurements. Coming to instrumental analysis.
Excuse me, sir. Excuse me for the interruption. Sorry for the interruption, sir. You have to share the slides again.
Which slide?
Yeah. Sir, you have to stop sharing.
I'm unable to hear you properly.
I told you.
Again.
Man, Goria, stop presenting. Sir, please stop sharing and again share your slide. Because somebody interrupted.
Again. Should I to start again? Stop.
No, sir. From that slide only.
Are you audible? Am I audible?
Yes, sir, you are audible. Just
If you
present.
see my screen? Hello?
Share the presentation again, sir. Go to present now.
No, actually, I was just.
इनका present एक बार किसी ने Sir, on the right hand side, present now.
Yeah. Is it okay?
Yes, sir, it's okay. Now you can. Yes, sir, it's okay. Now you can continue.
Okay, types of analysis. This is the slide you wanted?
Yeah.
Okay. Now, as already talking about the types of analysis, it is a quantitative analysis and qualitative analysis. So, quality is nothing but it is the materials of the species that is present in the samples. So, you need to identify or mark the quality of the material that is present in the analyte. When it comes to quantity, you need to analyze the relative amount of the substance. This is the relative amount of the substance in all species, for which you need to analyze. So qualitative is nothing but you need to quantify the material in terms of percentage, ppm, or some other parameter where you need to quantification. Sorry, it's not parameter, in a quantity. You need to highlight in its quantity, in its composition. Now, the wet chemistry is a very important tool of analytical chemistry, and in which this is interrelated with the instrumental techniques. Wet chemistry is a very important technique where it is the basic fundamental ideas are given, and it is almost ancestor of our analysis. You can, because now the advanced genes may be modified, but our grandparents or our forefathers are very strong in it. So some methods in instrumental techniques you have to utilize wet chemical methods. Unless and until you do not go for a wet chemical methods, and instrumentation may also fail. What is instrumental methods? Instrumental methods are those methods in which a certain characteristic property of the elements, molecules are generally taken into account, and they are analyzed by taking into a certain property of the element. It may be a physical property or some other chemical property. Now, you might be heard about thirsty cow in our childhood days. Previously, this is the cow. This is the cow. In previous days, it used to bring the thirsty cow was thirsty. It used to bring the pebbles and used to put it in the container, and the water used to come. And there's a lot of toil, sweat, everything they used to do, and at least they used to drink the water. So now generations, this is the modern analytical technique. We can simply compare where it is using the straw. The water is same, the pebbles are same, the pot is same, the person is same, but the method is changing. The method is changing where instead of putting the pebbles, he is using some straw so that it can be easy for doing certain analysis, or you can just go for an advanced techniques by just modifying the methods, but the theme of the chemical reactions, the theme of the basic fundamental ideas remains the same. The analytical chemistry is not a separate branch of chemistry, but is application of updated. This is the updated knowledge, updated chemical knowledge, and is widely used in the fields of chemistry. Methods you can just see by this characteristic property. The characteristic property like emission of radiation, absorption of radiation, scattering of radiation, refraction of radiation, diffraction of radiation, rotation of radiation, and electrical property of radiation, and some several other techniques are also there by just using the characteristic property of that particular element or particular reaction. See, if suppose it is an emission radiation, the emission spectroscopy like X-rays, UV visible, fluorescence, and Usher methods are generally applied. For absorption radiation, the absorption radiation also include an absorption technique of by utilizing the energy levels and quantum levels, where the difference in the absorption and emission is generally observed. And it is quantified and the material is analyzed according to this physical property. The scattering of radiation is also important. It is used in thermometry, nephelometry, Raman spectroscopy. Now coming to refraction of radiation, that is refractometry, interferometry, and diffraction of radiation, it comes into the XRD crystals. This is XRD, diffraction, X-ray, XRD techniques are generally utilized in this method. Diffraction of radiation, XRD, XR is also used. We will be looking after this method, XRF methods. This is called X-ray diffraction studies, and this is X-ray fluorescence spectroscopy. Now we can take one more chemical characteristic property of an element or a molecule by method of rotation, where you can calculate the polarity, optical rotation dispersion, molecular dichotomy. And this is also an important is electrical potential. Electrical potentials, the potential difference in which this potential or potentiometry plays a very important role. This is a very important technique, potentiometry, and by using certain amperes, conductometry is used. But in this method, we are utilizing this potentiometric method and chromo-potentiometric method. If you are using electric charge, this is a coulometry. If you are using electric current, it is an amperometry and polarography. And when it comes to the electrical resistance, it is a conductometry. This is widely used, and previously I have said the potentiometry is also widely used in the chemical analysis. Now, coming to the mass analysis, it is by gravimetry. You might be wondering why gravimetry is a classical method, but by utilizing this quartz crystal microvalence, the mass can be analyzed in this advanced. These are the big, quite advanced methods where the mass is analyzed in an instrumental technique. This is a mass by charge ratio of any materials are coming under the mass spectroscopy. Coming to rate of reaction, this is the kinetic methods are also seen. Now coming to the thermal characteristics. The thermal characteristics of the thermal gravimetry, titrometry, differential thermal analysis, that is called as DTA, thermal conductibility methods. Now coming to radioactive methods, this is a very important method where it is used in Baba Atomic Research Centers and certain radioactive in Kudankulam for power projects. Then radioactivity, it has been analyzed by two methods, that is activation analysis and isotopic dilution analysis. These both are very important for the analysis of materials. So finally, we are concluding, not concluding, we are finally discussing that by taking a simple property of an element or a molecule or a certain physical properties or certain characteristic nature of wavelengths or a certain characteristic of radiation, these methods are modified and it is being estimated or it has been analyzed by modern instrumental methods. But the fundamentals remain the same as the wet techniques. Hello? Am I audible? Hello?
Yes, sir. Yes, sir, you're audible.
Don't miss my screen.
Yeah, so you have to, I think you have to, you have to share the screen again. Again, we got interrupted.
What is this happening? It's not from my side.
I know, actually,
It's hanged up.
again, and again.
My options are not coming actually. Am I audible? Madam? What point is not?
Yes, sir, you're audible.
The instructions is there. Actually, PowerPoint is not working.
Yeah. Actually, we got interrupted by one of the participants. Because of that, your sharing got stopped. I'm sorry for the inconvenience, sir.
It's okay. The problem actually is not highlighting.
Highlighting is it? Can you start at the present? You can first share your presentation from present now, and then. So are you unable to present or share your PPT? Sorry for the interruption, everyone. Please wait for 2 minutes. Uh, so will be telegraphed.
Hello?
Yes, sir.
Hello?
Yes, sir.
Okay. Is it visible?
Yes, sir.
Correct, madam? Hello? Am I visible?
Yes, sir. Yes, sir. You are visible.
Is it okay, clear?
Yes, sir. Your screen is also visible. Abhijit Thakur,
Screen is-
you can switch off your camera.
Pardon?
No, no, sir, not to you.
Okay, pattern, madam?
Yes, sir. I can see.
Is it okay?
Think different. I can see the screen. Think different.
Am I audible right now?
Yes, you are audible.
Just a minute. Am I also visible now, madam? Can I forward?
Yes, sir.
Okay. Just talking about about this thirsty crow regarding this advanced analytical techniques where we have been utilizing just this simple analytical tool. You are applying a simple analytical tool to this and you're modifying the methods accordingly. Already I've shared the screen and I would go to this analytical chemistry slide also, this one. It is just an updated chemical knowledge. It is widely used in the fields of interest. This was covered emission, absorption, scattering, refraction of radiation, diffraction of radiation, rotation, electrical property. Am I right, madam? I have completed this now?
Yes, sir.
Thus, by taking the electrical charge, the method is said to be a colorimetric method. The electrometric methods, and chronography. By taking the electrical resistance, it is called as the conductometry, and the mass measurement generally measurements the mass to charge ratio. This is the mass to charge ratio. Use the mass spectrometric measurements. Coming to rate of reactions, these are the kinetic methods. Now, thermal characteristics like thermal gravity (dTA) and thermogravity analysis, everything is coming under thermal characteristics. But taking into account of the thermal behavior of an element, these thermal characteristics are these methods are generally classified, or it is being organized, and you can just do that technique. So I have talked about the radioactivity also. Now, for any analysis, you have to follow a particular strategy, methodology, and you have to apply it, and accordingly you can analyze any materials. So, coming to that, you have to select a method. First is you have to select the method, suitable method you are having, and after selection of the method, you have to select any which method is actually suiting you, whether spectroscopic methods and X-ray methods, or electromagnetic radiation, by utilizing electromagnetic radiation, by using this current, and by using potential difference. You select a method where you need to analyze a sample. Now acquire the sample. Sampling. This is a sampling. Sampling is very important. In a particular reference journals, or you can just see a particular reference book, a meaningful sample will end with no conclusion. If your sample is not proper, and if you are not provided a proper sample, the analysis of no use. You are just wasting the chemicals, you are engaging the chemists, or you are just a wastage of everything. So acquire of the sample, and what you call as the sampling technique is very important for acquiring the sample. Which type of sample you are sampling? It may be air sample, water sample, or soil sample. So methodology should be applied for acquiring the sample, and sampling techniques should be stringently followed. Now, coming to the process of the sample. Next, you need to process the sample. Whether the sample is in some dirty, is it in rock form, or it is in a crusted form, or it is a powder form. So you need to bring everything into a certain level where you need to process the further sample. For example, rock samples, you need to process it. You need to collect the suitable rocks, and you need to powder the sample less than 300 mesh. Or sometimes 400 mesh will be fine for any geological samples, but generally this will do our analysis. Now, coming to, is sample soluble? Next, after coming to this process of the sample, you should analyze that the sample is soluble. If it is soluble, in which media it is soluble? If not soluble, what you should do? If it is not soluble, carry out a chemical dissolution. The chemical dissolution may be some certain solvents may be used, like sulfuric acid, some HCl, HNO3, some strong oxidizing agents, or perchloric acid, hydrofluoric acid, etc. Or few materials can be used for dissolution, for chemical dissolution of the sample. Now, you can measure the property. After that, you can measure the property. If the property is not measurable after dissolution, then what you should do? You have to modify the method to change the chemical form. example, if nickel is analyzed, it is analyzed with nickel dimethyl glycine, DMG. Or for fluoride, you need to analyze fluoride. SPA DNS method is very suitable for which is having a high accuracy and in measuring by spectrophotometric methods. These are the good spectrophotometric methods. I mean to say that the analyte, that is the nickel and the fluoride, you are changing the chemical form and you are complexing it in certain other nature so that it will give a particular absorption and you can just measure the quantity. Now, coming to you need very important is the elimination of the interferences. You need also interference of certain parameters also coming under, in the analysis. So you need to eliminate the interferences of any external matrices that is present in the analyte. The measurement property is desired. Any other method, first you see what measurement property is desired. Okay, then calculate the result and quantify it, and you estimate the reliable and reproducibility. This is very important. You are just ending with a sample, with just titrating and you're just giving the sample without a reliable method is of no use. I don't agree. If your repeatability is not good and your reproducibility of your test is not good, it's of no value. So your test result should be reliable. That means you have estimated mean result. At least you should get the alpha levels, the K2 levels. K level should be the confidence level should be the K2 level should be at 95 and above. 95%. You should have a confidence interval. This is called confidence interval. Below that, I don't agree. So 95% of confidence interval are more than in some cases 98% is also confidence intervals is noticed. I mean to say simply that if an analytical chemist or a particular chemist is analyzing the sample without reproducible values or without repeatability, it's of no use. Now, application of analytical methods of pores, minerals, and few environmental samples. Today, I will be discussing about a few methods like XRF, spectrophotometric methods, and atomic absorption spectroscopy. This comes first, this comes second, and this is the third one I have kept in order. Then XRF, this is XRF, XRF, X-ray fluorescence spectrophotometry. And this is spectrophotometric methods and AAS. These are the few techniques in which we will be looking after a few analysis and this some examples, 1 and 2 example, we will be looking after certain examples, and this we will see what are the, in detail we will be seeing about the XRF and AS. Now, coming to the definition of ore and mineral. Ore is a natural aggregation of one or more mineral that can be mined, processed, and sold profit. So ore is a definition where it should be mined, it should be processed, where we are doing, and sold at a profit. In the process is a complex thing where the material has to be upgraded to its finest quality and to be sold to the industry for extraction purposes. Now, we very well know that all ores are minerals, but all minerals are not ores. So let us see certain important ores in our day-to-day life, and most of the literature has been saying this: carbonate ores, sulfide ores, oxide ores, sulfate ores, silicate ores, phosphate ores, spinels. These are mixed oxides, are certain combination of materials, that is in form of radicals. For example, carbonate, CaCO3, or some other carbonate ores, or lead carbonate, magnesium carbonate, Epsom salt. So limestone, dolomite, siderite are the examples of a carbonate ore. So in this ore, the methodology will be different. in the analysis. The carbon the methodology applied for the analysis of this carbon is a little bit different from some other compounds or ores. And the methodology that is applied in sulfide will be different. Oxide will be different. Sulfates will be different. Silicates will be different. So it is very important that an analytical chemist should understand the basic chemistry, and for a number of trials and a number of research articles to be he has to go through, and he should be able to understand what is the basic structural chemistry or reactivity in that so that in that particular ores or minerals or some any chemical analysis. Then only he can able to identify a suitable analytical technique. Now, this is a Mohs scale of hardness, where the hardness of any material are generally identified by its 10 scale grading, and moreover it is also modified by one of the recently published articles where I have just gone through. It is a magazine of Discovery magazine, where it has been extended up to 12 units. I'll show you the next slide. First 10 is it is a very hard surface. The diamond is very hardest, and recently we have seen much more harder than diamond is also been published in certain research articles. And the 9 is corundum. Basic, depending upon the hardness of any material, with respect to this reference, these are the reference. You will be calculating the hardness of any materials. It is on the Mohs scale or Beaker's pyramid. Some metals can be analyzed in Beaker's pyramid. Hardness in minerals. We are talking about minerals, so we are taking in the account of Mohs scale. That is 10 is diamond, 9 is corundum, 8 is topaz, 7 is quartz, 6 is microlene, 6 is microlene. These are ectosilicates. Microlene is a ectosilicates, and apatite, it is a phosphate minerals. Apatite is a phosphate minerals, and fluorite, this is a calcium fluoride minerals. When you come to calcite, this is also calcite. This is also calcium-based components. Gypsum, calcium sulfate, and talc. Talc is nothing but it is a clay mineral containing magnesium silicates. That is Mg2 SiO4 410 times OH twice. This is nothing but a talc. So it is very finest. It is very fine in nature. So it is given as one Mohs scale hardness. So the hardness increases. The hardness increases with this side. So hardness increases. Now I just talked before the updated where the hardness is carried out to 12, where it is 58% greater than diamond. This I just shared a screen for your further references. You can just go through. It takes quite a little bit time. And I just want to give a small example. In previous department I worked in military explosives, where they used tungsten carbide. This is tungsten carbide, W4C3. This is the very strongest, and it is used in armor piercing in battlefields. Now, in battlefields, it is used in the armor piercing armor. It is very hard. So the hardness of the material of tungsten carbide is very high. And moreover, you generally know the diamond is very hardest. But this is the nitride compounds and carbide compounds are much more harder. Industrilite. This industrilite are a meteorite which is just coming from the space, and we have came to know this is one of the hardest material. This is 58% greater than diamond. Okay. Now we will be discussing about. You can just go through this literature where the talc is given and gypsum is given, and in between 0.5 they have increased, and they have just given this additional compounds where you can identify the hardness of material with reference to this Mohs hardness. Now, coming to the constitution of Earth. What is the constitution of Earth we are having? It is a 98.6% of the materials are only 8 elements. 8 elements. So out of the 8 elements, only one out of these 8 elements, the 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 elements. These are the 8 elements where it contains 98.6%. So the remaining 1.4%, this is the remaining 1.4% is this one. You can just analyze in ppms. This is very important and imperative to know that the oxygen is the first and foremost. It is present in every mineral, or it is present in any materials. So it is in form of oxides, carbonates, in anywhere. And moreover, the next is the silica, then aluminium, then iron, calcium, sodium, etc. Magnesium, as per the availability in the earth crust is being given in the earth crust. So the highest is the oxygen. Now I can just share one more important slide from one of the reference material, where you can just see the abundance of the elements on the earth crust as per parts per million. You can just see the first place goes to oxygen, silicon, aluminium, iron, calcium, magnesium, sodium, potassium, titanium, hydrogen, and you can just go up to, you are given up to 77. Just go through the material and you can able to identify what is the abundance, the relative abundance of the available atoms that are present in the earth crust can be find out from this reference materials. And let us see, we are talking about the minerals and some certain other rock forming rocks. That is nothing but, it is a mixture of minerals. Rocks are nothing but a mixture of minerals that are present in our earth crust. So minerals are the largest amount of the world in millions per ton. And what we are using, we are just excavating and utilizing for our general needs. So let us see which is the biggest mineral what we are utilizing is coal. Now coming to crude oil, iron, sodium chloride, etc. You can just check out. And the coal, these are the mostly utilized as a fuels or some other materials for iron ore is also present in the third position. And coal is one of the richest, it's not the richest in consumption. We are talking about consumption of in the world. This mineral, coal, crude oil, and this are vastly utilized in this world. These are the continuation of the previous slide. Now let us see the property of electromagnetic spectrum. Property of an electromagnetic spectrum, where this can be utilized in the analysis of several compounds or elements. So you can just see electromagnetic spectrum is spanning from, it is having a wave and a particle nature, and is having a, generally it is having a wave nature, it is having a certain wavelength, and having this particle nature, it has certain mass in certain characters. Certain, now you can see there are in electromagnetic spectrum is from 100 megameters to -6 nanometers. So the wave of this electromagnetic spectrum is you are containing the low, high wave is the radio waves, and as we go on to the top, the wavelength is decreasing and the intensity of the radiation is increasing. So we will be utilizing the microwaves processes in certain digestion process. We will be utilizing in some digestion process. The microwave techniques is also used in some digestion techniques. And you very well know far infrared techniques, the IR techniques are utilized in certain modes of IR spectrum used in the IR spectrum. Enhance of spectrum of one. Also used the properties used analyzing the elements of this red, indigo, blue, green, yellow, orange, red, which are. And I will be talking about the X-rays. X-rays can also be like for the analysis of materials. It can be used for materials or several other applications are there for X-rays. And even gamma rays are also used in the analysis. Then the food preservatives, it is used. Okay, gamma rays is used. X-rays are used in mineralogy, ores, food industry. It is also used in food industry. It is used in foundry industry, metallurgy. That is foundry, metallurgy, etc. Several applications are seen. Now we are coming to the one of the aspects of our spectrophotometric methods. I'm extremely sorry. We will be discussing about the three methods of analysis. Right now, we are dealing with the X-ray methods. Now, X-ray fluorescence method is also used in chemical analysis of certain minerals and several other unknown elements. Its application is widespread in modern methods. By utilizing these X-rays, we can analyze the materials. This is a pressing machine. I will just go through afterwards. I will explain about this machines. This is a machine, how it looks like. X-ray fluorescence spectrophotometer. Now let us see what are the basic theory of X-rays. When a beam of X-ray falls on a sample, the atoms become ionized and move out from its stable original place. The X-ray beam ejects the inner electrons from the inner shell of the atoms. Then what happens? When the electrons comes from the inner shell, it will occupy the when the electrons comes from the inner shell of the atom, there is a vacancy, there is a space vacated. So the high energy electrons will try to occupy the lower energy levels, thereby emitting certain radiations. That is X-ray radiations, and that is called a fluorescence spectrometry, where if the X-rays are passed with certain wavelength, and fluorescence will have a maximum wavelength. If the wavelength of the incident radiation is lambda, and the fluorescence X-rays will be having a higher wavelength. This is called fluorescence spectrometry. The intensity of fluorescence, now I already explained about that. The intensity of fluorescence depends on the quantity of the analyte that is present in the sample. So if the analyte is containing more amount of sample, more X-rays will be produced, and more quantity of fluorescence, more amount of the fluorescence has been measured and it has been quantified. So the percentage yield can be measured by this technique. The measurement of fluorescence intensity, you have to know what the fluorescence intensity makes possible to quantitative determination. So if the material is more, and the X-rays are falling on the material, if for example, 50% of the material is uniform material, some material, that is, for example, you say if it is tungsten, or you say it's just like manganese, it will be producing X-ray fluorescence radiations, which is equal to the quantity of the material. So more fluorescence is seen from the manganese. Let us see the schematic diagram of fluorescence. Now this is hitting an electron, and the innermost X-ray is hitting, this electron is ejected. And when the electron is ejected, this will fall into the lower lower energy levels, thereby emitting a characteristic X-rays. Shall we see once again? We shall see once again the incident ray is hitting this electron. This electron is being emitted, and there's a space in between, so the electron will be occupied at the lower energy level, emitting radiation. That is, a characteristic X-ray is ejected of the particular atom. And you can see several spectral lines, that is K alpha, K beta, K alpha, K beta, L alpha, L beta lines in several atoms. If the atoms are less than 23, there is only two spectral lines, that is K alpha and K beta. And if it is greater than 23, it has K alpha line, K beta line, L alpha, L beta. So you can know along with this material, this X-rays are being generated and X-ray fluorescence can be measured. Now, coming to the instrument, we are talking about the principle, instrument, methodology, where it is applied, and how the material is being quantified. Now, the instrument contains the X-ray generator, simply X-ray generator, and a sample tube, sample chamber, collimeters, spectrometers, analyzing crystals in WDXRF. This is only available in analyzing crystals, are only available in WDXRF instead of EDXRF. What is EDXRF and WDXRF? This is wavelength dispersive X-ray fluorescence. This is energy dispersive X-ray fluorescence. So in this method, these crystals are not utilized but in WDXRF, the crystals are made utilized for analyzing a particular radiation of the sample. And the radiation which is coming out of the crystals are collimated, passed through the recording, and it is being counted, and quantification can be done accordingly. Now coming to the principle, what is the main principle? Already I said, the wavelength of a dispersive detectance physically separates the X-ray according to their, X-rays will be separated according to their wavelength. The X-rays are directed to the crystals, and the emitted radiation that is coming from after the hitting a particular sample, it is being diffracted with a suitable crystals that is available on a goniometer. And it is diffracted and it is analyzed by the Bragg's law. The Bragg's law is very famous, and you will be n lambda is equal to 2d sine theta. If, for example, if the spacing, d is the spacing of lattice, n is the order, and l is the lambda is the wavelength of this. So 2d sine theta, it is being obtained. So I will talk about the incident rays where it is having less than 10 degrees, 0 to 10 degrees, 170 to 180, the measuring angle, 180 degrees, the measuring of X-ray detection. X-ray detection will become a difficult task. So generally, 20 to 170 is 20 degrees to 170. Precise goniometers are available, and the crystals will be diffracting the particular emitted X-ray radiation, the fluorescence radiation, the X-ray fluorescence radiation is visible in 20 to 170 degrees. Now you can just see, as already said, this is the radiation, and this is the normal, and this is the angle theta, and this will be according to the 2 theta. This is the number of n in the order of the spacing lattice of any crystalline structures of foreign materials. You just see there is an incoming radiation of X-rays, and after hitting this particular element, the electrons, the ejected X-rays will have a longer wavelength. For example, it is having a wavelength. This will having a wavelength or different. This is called a fluorescent X-rays, and by identifying this, the fluorescence can be, the material can be quantified. And this is what you call it. This is a characteristic of each and every material. This is a characteristic of a material, of a particular material. No same material will give a different lambda values. Now we should able to understand. I already said this is the fluorescence, Rayleigh scattering, and Crompton scattering. So when X-rays hit the materials, the radiations with the X-rays which are generated with maximum wavelength is fluorescence, and which is having the same wavelength, which is called as the Crompton, and which is having a different wavelength is called a railing scatter. Now the schematic diagram, the railing scattering is, the lambda has no change in its value. But Crompton scattering, the value will be deflected by its original path, and it is quite different. Now coming to WDXR, this is wavelength dispersive X-ray fluorescence. Now coming to the schematic diagram, this is an X-ray tube, this is an X-ray tube. There, the X-rays are falling on the sample, which is placed in this. The sample may be present in holders or certain material, certain cups or holders where it is allowed to, the X-rays are allowed to fall on that material. And after the injection, the primary collimators are present, where I already said there's analyzing crystals that are present as per the user's choice. The crystals can be taken during purchase of the instrument. And finally, a detector is present and the signal is amplified, and it can be calculated, the quantity of the material. So if the quantity of material is more, the X-ray fluorescence will be more, and the signal generated is being quantified, and it can be calculated. This you can say this is a goniometer having a different crystals which is rotating in 360 degrees, and different crystals are present. This is going and hitting, collimated, and certain crystals are there. This is the detector is present. This is also the different view of the thing. Now, coming to the main components of X-ray. X-rays contains an X-ray tube. The X-ray tube is a vacuum tube. It is a vacuum tube which contains a filament and an anode target. The filament and an anode target. Generally, there is anode is generally made up of rhodium, tungsten, copper, molybdenum, rhodium, etc. Several iron materials are made as this one as an anode, and a cathode is responsible for this thermionic emissions. This is thermionic emissions. Like tungsten or molybdenum is generally used as a cathode, where this is used to heat the filament with a vast potential difference, and with generally our machine is working on 4 kV kilowatt. The electrons will be generated from this and hitting this anode target, thereby generating X-rays. And these X-rays are being collimated with a beryllium window. Why beryllium window is used? Beryllium window is a very clear and passes X-rays. Beryllium window is generally used because it is transparent. It is a transparent, and it utilizes. It allows the X-rays to pass through this beryllium window. This is the main. This is present at a high vacuum, and in this, an argon is also filled sometimes. Sorry, that is about argon is filled in detectors. I'm sorry. In the X-ray generation, this entirely vacuum is present, where the electrons are accelerated towards the anode end, and it hits the target, and the X-rays will be produced. Now I'm talking about the analyzing crystals. Analyzing crystals utilize the dispersion of X-rays. These crystals are called as analyzing crystals. Certain analyzing crystals are lithium chloride, PET, topaz, and some other crystals may also be used in this analyzing crystals. Some tartrates crystals may be used, and in case several crystals can be procured. The PET crystals can be used. This is the PET crystals, lithium fluoride, and some tartrate can also be used as a crystals where it can diffract the coming out electrons, coming out X-rays, and can be collimated into the detector. Now coming to detector, mostly we'll be in this X-ray fluorescence techniques, we'll be using this gas-filled detectors and scintillating detectors. So detection limits of lower atomic masses is required, this gas field is applied. If a higher mass is required, scintillating the detectors are generally utilized during the detections of the X-rays. This gas filled in argon is filled in this chamber for detectors, and this contains a beryllium window where our sodium chloride PMT crystal windows are generally present in order to pass the X-rays into the detectors. Here, this is the beryllium window where you can see this is a beryllium window. This is the photons of the X-rays that are generated, and they are given what you call as a space at different. This one, the gas field in the scintillating detectors, where the electrons are emitted from this and are multiplied, electron multiplying tube, and the signal is amplified and then detected. Comparison of detectors is not required. Now, let us see what is the difference between the ED WDXR. This is already I said it is energy dispersive X-ray fluorescence. This is wavelength dispersive X-ray fluorescence. Now, for energy dispersive, you can utilize from sodium to uranium in modern periodic table, that is 23 to 92, and this is beryllium to uranium. So you can use for lighter elements also. This less optimal for light. This is less optimal for light, and this is for heavier elements. If you are choosing from broad spectrum, and this WDXRF is best suitable when it is compared with EDXRF. It is costly enough. This is costly than this technique, and relatively it uses a high power consumption and relatively expensive. I already said it is good for light elements and it is less optimal for heavy elements. But this option is optimal for light elements but good for heavy elements. Now coming to methodology. Now we will be discussing about the methodology. First, we have talked about what is the principle of X-rays. We have talked about the instrumentation, what are the components that are present in the X-ray technique, X-ray fluorescence techniques, XRF, it is called as WDXRF, wavelength dispersive fluorescence technique. Now we have discussed about this, and we will go to the methodology. Methodology, this method is called as non-destructive technique because the sample is not being destructed. Most of our chemical methods or certain other methods, we will be changing or modifying the nature of the original sample. But in this method, the nature will be remain as the same and it can be reutilized. Normally we do not reutilize, but it is called as a non-destructive technique. So let us see what are the methods that are analyzed. Mainly they are analyzed by two methods, that is pressed powder method and glass bead method. What is pressed powder method? Just a minute. In this method, the sample, rock sample is put for 300 and if possible to 400 mesh is also suggested, but 300 will make sufficient, and it is pressed with 20 to 30 tons. Already I have shown you one machine at the starting. There is one machine, and left of that is a powder pressing machine. It is a pellet making machine. It can be pressed material, and along with if the material can be pressed into pellets, it is quite sufficient enough. If the powder material, that is the sample, is converted into powder, and the powder can able to bind it properly, there is no need of certain external binders. But some binders are also used like starch, boric acid, potassium chloride, and cellulose. It should be compressed with 20 to 30 tons of pressure, and it is made into a pellet. Sometimes you use a starch, boric, and normally we use a boric acid to compress the pellets with 20 to 30 tons. And if it is not possible, if it is breaking, certain polyvinyl acetic acids and polybutyrate, that is perspex materials, can also be added to the sample, and it is made finally, and it is compressed into pellets, and the pellets should be further gone for the analysis part. Now, take 1 gram of the sample, mesh it, and this is a fusion method. This is the second method. This is the powder method. This is a procedure for the fusion method. The platinum crucible you are taking, and the second method is glass bead method, where you add 4.8 grams of lithium tetraborate. Lithium tetraborates and lithium carbonate of 1.2 grams is generally added. And a minimum property, and this chemicals what you are using, which is used for conversion of this glass bead. Glass bead is nothing but the material will look like a bead which is transparent in nature. Transparent in nature. This transparent in nature and this is transparent in nature, and it forms a glass bead after making melting with this lithium tetraborate and lithium carbonate. And sometimes you can add certain non-wetting agents like ammonium bromide or cesium bromide may also be used. Bromide can be used as a non-wetting agent. Choose the content. Now you take the sample, you have taken a crucible, you have taken 1 gram of the sample, kept it in, and you have added the fluxes. These are called as fluxes, and made to heat on the Meeker burner. It is made into uniform, and a mold is being taken, and this is poured, and it is a circular. It is in circular man, and forms a. You can form pellet. Bead. You can just get a transparent glass beads. This is ammonium iodide or cesium bromide or ammonium bromide. Ammonium iodide can also be used as a non-wetting agent. At around 1100 degrees centigrade, first you need to, this is a Meeker burner, not a Bunsen burner, it is a high temperature, or sometimes if it is not suitable, you can go for fusion methods by induction melting of the solids, or you can use by you can go for induction based, or you can go for a furnace heating, and you can make into this glass bead. And the glass bead is further analyzed for X-ray fluorescence methods. X-ray fluorescence, and the quantity of the material that is present in that can be measured. First, you are taking a material and you are converted into a glass bead. And the first method is you are taking the material and you have made into a pressed pellet. The few fluxes that are employed are lithium tetraborate, lithium metaborate, sodium pyrosulfate, so potassium pyrosulfate, and lithium carbonates. Generally, these are called as fluxes with high purities. High purity should be taken for preparation. Now, this is the glass bead. What I was just talking, cesium bromide can also be added. The glass beads is an important and popular technique for an accurate analysis of various refractory samples. Now you have to take a cesium bromide or ammonium bromide is also applied for non-cracking agents, like sodium sulfate is also added for non-cracking. Suppose if you form glass beads, it may have a chances of cracking. So in certain cases, you can take the sodium sulfate, which can be best suitable for non-cracking agent, and generally a diameter of 330 into 40 into 2.30 dimension of this bead is generally poured into the mold. You pre-mold and is carried out for XRF analysis. Already I said regarding this beads, I can just skip out this. Now, coming to the industrial applications, what are the industrial applications of XRF? This is the mining, like foundries. Some foundries can just modulate by taking the sample into the XRF and analyzing how much percentage of the material is present, and so that the production can be taken by adding adding the particular components in the metallurgical industry. So this is also in the metallurgical industry. Also, you can metallurgy. So this is in mining and minerals. Also, it is used in analysis of. It is a non-destructive technique and a versatile, simple. In metals, that is in metallurgical industries, directly the production units are having XRFs. The production units are utilizing this XRF techniques in order to manipulate or in order to compounding the materials. Compounding the materials in the sense if they need some certain additives. If you want to additive directly, some like carbon or vanadium or some other additives to be added directly, the material can be taken from the foundries, and it is very versatile instrument, and the composition can be calculated or it can be analyzed. In cement industry also it is used, in polymers industry, food, paper, and bulk commodities and other is also used in these techniques. And we are talking about the chemicals or the ores and rocks. Ores and rocks. What is the versatility of XRF? Why it is widely accepted, and most of the industries, they want the analysis in quick time, reliable and reproducible, and it should be very simple enough. So it is a non-destructive analysis, as already I said. It is a minimal and no sample preparation. It is very simple. You need not to go for sample dissolution techniques or converting the matter into certain other forms wherein atomic absorption spectroscopy or photometric methods are applied. This is a no or a minimal sample preparation is required simply by taking the purest form of this, converting into the beads or pressed pellets. This is a rapid and simultaneous multi-elemental analysis is generally done in this method. It is used by a non-technical staff. It's very important, and you can just understand. It's a very simple technique. Anybody who can lay down the SOPs, standard operating procedures, we can able to operate this machine. It is not a big challenge. It's not a big task, but interpretation of the results should be done by the specialist or the analytical chemist, which dealing with the particular analysis. It is analysis on solids, liquids, powders. So you can do on solids, liquids, and some powder films and granules. So it depends upon the usage. Wide dynamic range from ppm to 100%. Once you go for the XRF, the elements can be analyzed from ppm levels to 100% with K2 levels, that is 95%, 98% confidence level intervals. 98.5. Okay. Qualitative and quantitative investigation also can be done, regular or irregular shapes. So you can go for a regular shapes or irregular shapes. If your material is of iron fillings, if your material is a rock, if your material is a rock, if your material is a slag, if your material is a what do you call as ash, any material can be utilized for the analysis of this XRF technique. Used in industrial and environmentals, no potentially dangerous chemical. This is very important. This is very important. Where there is no potential chemicals are generally used in this methods. Generally, if you want to know the dangerous chemicals, or I just want to share my knowledge, and whatever I had, just for the benefit of the nation, I am very much interested in chemistry, first point. So you have to love your chemistry, the basic concepts. You should be clear about your fundamentals. And second, implementation and applications. Now, coming to the dangerous chemicals, you can just go through any website, MSDS, Material Safety Data Sheets. This is a material safety data sheets of any chemical. If you want to know the toxicity or hazardness or the total problem, what if there is any problem with the sample and how to deal with the particular chemicals, you can go for an MSDS. You just type MSDS of any chemical. For example, I want to know about sulfuric acid. You just type MSDS, sulfuric acid, all the material safety data sheet will be generated. For example, if I want to know about hydrogen fluoride, HF, what is the problem with HF? It is very dangerous chemical. Once, if it touches your body, it will penetrate into it and it will react with the calcium. The hydrogen fluoride will replace the calcium of your body and bones and teeth. So, in that case, you need a glutamic acid, glucanates. HF antidotes should be used. What are antidotes? Antidotes like calcium gluconate, CIUM, glucanates. Calcium gluconate is a good antidote for HF. So your laboratory should be well equipped with this antidotes if suppose any accident occurs. So I'm just deviating from, I wanted to share this important aspect. That's why I've just given this, because of the safety of the nation, the safety of our, safety is also our pride. If you're safe, everything is safe. Be safe. Now, there is no dangerous potentially no dangerous chemicals in this. A simple pyrosulfates is taken, lithium borates is taken, and that is used for XRF analysis. No requirement of fresh calibrations. Once it is calibrated, it can be utilized. It is a well-respected technique all over the world. Okay, this ends up our X-ray methods of analysis. There is X-ray fluorescence techniques, which is a very wonderful technique we can utilize of. The second method is we will be going with very modern methods of analysis. Of course, it is also introduced very much previously, but it is nowadays it is applied in the field of chemical sciences, and if the elements or the analytes, what you want to analyze is in the low concentration mode, these methods are applicable by utilizing the radiation phenomena. So let us see what is the atomic absorption spectroscopy. This is a simple schematic diagram where you can see this is a instrument where you can see some instrument after combustion of these materials, some of the fumes will be going through this and it will be vented out through the outside. So this is the main reaction chamber, and here some of the components are placed. Let us see in detail. This is the instrument, Perkin-Elmer, where it contains a source of radiation here. This is what you call as main important cell. You can just call it as a reaction cell, which contains several components. In which you can check it. You can have a look in detail in further slides. Now, after here, event is generally present, and what are the toxic gases and what are the flames that has been the toxic gases, or what are the flames and unburnt fuels, everything will be drained out. This I will explain you later. This is a Perkin element model with atomic absorption spectroscopy with hydrogen generator. They are having 11 elements in which silver, arsenic, cadmium, cobalt, chromium, copper, iron, molybdenum, nickel, zinc, lead, etc. are analyzed. And in addition to that, several other elements can also be analyzed. We are equipped with this. Several other can also be utilized by acquiring some sources. The source of this is hollow cathode lamps. So you have to purchase hollow cathode lamps as per your requirement. If you want to single source, this is a single source where the interferences will be very less, and you can utilize this for this atomic absorption spectroscopy. Now, the principle of atomic absorption was known for about 150 years. It was put by the analytical chemistry by an Australian physicist Alan Walsh in 1950. Now it's a very simple. Just before going into the entire principle, I'll simply explain you. This is a radiation. For example, we are considering electrons in the stable state and the ground state is here. The radiation source is coming and hitting these electrons in a stable state, thereby the energy is absorbed and this is excited. The electrons will be reaching to the stable ground state to the excited state. And after some time, this is by absorbing radiation. The radiation is absorbed and it is excited. So the excitement of the electrons due to the absorption of the radiation, it is called the absorption radiation. And the electrons, when it is excited, it will come to the ground state, emitting some radiation, that is photons, which is having a particular wavelength, which is h nu, which is equivalent to the absorbed radiations. So already the absorbed radiation which has been excited, so it is being released by these atoms. So the important principle is that you need to atomize the sample. You needn't have to ionize. You should not ionize. Ionization is, ions are not desirable. Only atoms are desirable in this. So it is a challenging task in order to convert the analyte sample into an atoms. So you need to choose certain other aspects to convert the analyte samples into atom state by the methods. So this is nothing but it is given by a Boltzmann distribution law. It is the number of atoms in excited state, and this is the number of electrons in the ground state, is generally given by the Boltzmann distribution law, where G naught by G is the ratio of statistical weights of atoms that are excited state and the ground state. It is given by this equation, and K is the Boltzmann constant. Is the energy of excitation for the atoms to excite into the higher energy level. Now, K is the Boltzmann constant and T is the temperature in Kelvin. It is given by this equation, and you can relatively identify the number of atoms that are present in the ground state and the excited state. So our mode of interest is we need to excite those analyte samples into atomic state. And you can just see by a Beer-Lambert's law, for example, if this is a cell, or a simple cell I'm saying, but here the cell, this is a sample cell. If this is the radiation I0, if this is a radiation I0 is going to the sample containing some concentration, where it comes out with I, with absorption, with certain absorption. So decrease in this intensity of this radiation is measured by absorptions. This is the simple Beer-Lambert's law. Here the sample cell is a flame, not the cuvette. Cuvettes are used in spectrophotometric methods. So here the flame, what we are utilizing is a sample cell. So we will be utilizing this. So by utilizing this principle of the absorption of the radiation by the analytes which are present in the atomized state, which are passing through the flame, when it is in the atomized state, the decrease in the intensity of radiation is measured and is amplified, and it is recorded, and the concentration is measured. This is the simple principle behind this atomic absorption spectrometry. Now, before that, we need to calibrate the instrument by the known standards. You have to procure standards, and in this method, the source of the radiation is only single variation. That is, you are choosing a hollow cathode lamp of mercury, or of a certain specific element. Only a single radiation of same radiation will be passing to the sample. The source of interference is also very less in this technique. The calibration should be very important and a must before analyzing the sample. And so suppose if you want to analyze zinc elements or lead elements, we should have a lead hollow cathode tube. If you are analyzing copper, you need a copper tube. Okay, and the standards are also should be of particular dilutions, and you need to calibrate a curve with absorption versus concentration. It should be a straight line. If this is a calibration curve and with a particular limit, and the unknown is, for example, if it is coming here, and the concentration can be calibrated by this graph, and it can be analyzed. This is the principle of this. This is the simple what I was just telling about the Beer-Lambert's law. This is a cuvette. But in case of flame photometry, the flame is taken as what you call as a cell. This is what I was just telling about the calibration. Calibration of the machine is very important. Unless and until your machine is not calibrated, you will not get values. At every time of measurement, for example, you want to start a fresh analysis, you need to calibrate with the particular standards. The standards may be of NIST, National Institute of Standard Testing. NIST is very pure. It pre-analyzed, and it can be having a particular percentage composition. From that, you need to calibrate, and certain standard like CanMat, and certain Australian standards are there, Canadian standard is there, UK standards are there. You can just ask your choice. NIST is simple and is reliable, and these are also reliable, but your cost effectiveness NIST is much lesser. Now coming to the instrumentation. Instrumentation, we need a light source. Already I was just telling about the hollow cathode lamp and electrode-less discharge lamps. These are the two. This is one, and this is a two. This is the source. In order to analyze any material, you need a source. In this method, previous technique, XRF was a source. X-ray radiations are a source. In this, light radiation is a source. Where hollow cathode lamps are taken, and there may be a beam of radiation where it needs to be chopped, and a chopper is generally used to produce a single beam of radiation, radiations. Now, the sample or the atomizer, what I was just saying, it is a very important. This is the heart of the technique, where the flame, graphite furnace, hydrogen generator, cold vapor system, everything comes into this sample cell. This sample cell contains atomizers, nebulizers. All mechanical functions are there in order to change the analyte into atom state. So if you want to analyze the atom state, you need a flame also. If you need a flame, you want a fuel also. You want a fuel, you want also oxidant. The fuel itself will oxidant. If you have a fuel itself, you cannot burn. You need an oxidant. So you need a fuel, you need an oxidant. So the system is such a complicated that you have to choose in such a way which method and which technique is best suitable for your analysis, and what is the requirement of your analysis is very important. And moreover, the sensitivity of the instrument and the range of testing is also very important for the selection of the instrument and the components that has been installed and to be procured or procured from the market. And the fourth one is monochromators and detectors. In this also we will be seeing detectors, amplifiers, and readout cells. This is the instrumentation. Let us see the light source. Light source, as I already showed, there are two light source, that is hollow cathode lamp, HCl, and EDL, electrodeless discharge lamps. In this, a cathode contains circular. It is a cathode is contains of an analyte metal. This is contained in analyte metal with a cylindrical hollow cathode, and it is a glass cylinder filled with argon or neon. This is filled with argon or a neon to maintain an inert atmosphere approximately with a 10 torr. So the pressure of 10 torr is present in this. Generally, this is the 700 volts are applied. And this voltage is applied. Voltage is applied to these terminals. Generally, in which tungsten or nickel wire is present. These are generally made up of tungsten or nickel in order to produce what you call as a glow ions. It produces a high intensity of radiation where the inert gas ions sputter the metal atom. It is very important. The inert, it is heated up in such a way, this is heated up in such a way that the argon gas or the inert gas that is sputters the metal that is present in the cathode, and a beam of radiation is crossed. And generally, this also where the window is placed, generally a quartz cells are good for this is present in these windows. Hollow cathodes are fine, it is having a finite lamp. So it is because it is a continuous discharge of the element from the cathode, and the radiations are passing for the due course of time for consider for 2 years. So the life period is 2 years or 5,000 microamperes hours. So after due course of time, this will vanish. So it is very important that you need to change the light source after due course of time. Now coming to electrode discharge lamps. This electrode discharge lamp is similar. Here the electrodes are not present. As I showed, the electrodes are present in this. In this, there is no electrode, but you can say the electrode discharge, it is containing a small bulb in this. There, the material, not the material, actually it is made up of a bulb containing the material which contains the same element to be analyzed. And this is being sheathed in a what you call a ceramic holder. This is a machine. Ceramic. Before sheathing, there is a radio frequency coil. A high induction coil is circulated like this on the top of it, and this is placed on a ceramic sheath in order to protect her, and it is directed and to a quartz window. And it is externally a supply is being given for this. So this will glow, and due to the induction of the radio frequency coil, the atoms are the materials of the atoms are generated, and it will be passing through the quartz window through the flame, near the flame, and you can analyze it. This is electrodeless discharge lamp. Once you come to the versatility or which is better suitable for our choice, whether hollow cathode lamps or electrode discharge lamp. Everybody has an advantage, everybody has some disadvantage. Let us see what are the advantage. This is very sensitive, and can be analyzed for low concentration methods, low concentration of analytes. This is sensitive, and low concentration of analytes. Now we will see in detail, and let us see what is a chopper. Chopper is for a pulsating radiation of a light source emitting the interference from emitted light organized into the sample cell. So this will only allow the radiation to be only single beam to be passed into the flame. Now compared to sample cell. Sample cell is very complicated and you need to, it is a heart. You can just say it is a heart of AS. It is a challenging task in which a sample to be atomized, you have to change into an atom state. Atom state. The radiant energy, just a minute. The radiant energy of a specific analyte wavelength from EDL HCl, this is a hollow cathode lamp, passes to the sample, that is flame, furnace or quartz cell. In the ground state atom and produce a part of radiation, radiant energy is absorbed by the ground state analyte. So already I said in the principle that the atoms are excited to the higher levels by absorbing some radiation. The efficiency of atomization is a most critical process, and the sensitivity is determined and proportional to the ground state atom that is produced in the light path. So the sensitivity is dependent upon that is the most critical that it should be atomized, and the number of available analytes should be present in the path of the radiation, in the path of this radiation, so that the intensity will be decreased with the concentration of the atoms that are present in the flame. Therefore, it will be decreased. Hello? Now, laminar premix burner, before getting into the flame and the oxygen fuels will be driven by the nebulizers, eventually driven. Only 10% of the sample will be carried out, and remaining 80% of the sample will be drained out as a waste. So you can just imagine how the atomization takes place by the nebulizers in this manner. Now the temperature of the flame can be seen. The natural gas is this much. We can go through the literature like this. This is the burner system where, as I said, this is a burner system. This is a nebulizer. This is the sample will be inducing, and auxiliary. This is the nebulizer which carries the fuel and oxidants. And this will be driven out. This will be form of the mixture of fuel, oxidant, and the sample will be mixed, and it will be vaporized, and the flame will be emitted, and the atoms will be available in this phase. Now the laminar flow zone. This is a very interesting. This is a 1 centimeter burner length. I am just calculating. Here you can see this is the maximum oxidation takes place, and you have to be selectively. This is the area of interest where we need to analyze the atoms. It is being taken this laminar flow. This is the research article. I have taken this diagram from one of the research article, which was quite interesting, and it has seen the distance of centimeter with a burner tip, the accuracy, the available atoms. As we go on the top, the ions will be produced. So your radiation should pass in such a way. It should be atoms should be available in the path of the radiation. We'll be seeing the graphite and gold generated. We have lots of time. We are running less of time. We'll just skip through some of non-important things. The flame process contains the nebulization, dissolution, liquefaction, vaporization, atomization, excitation, and ionization. So the atomization is very important, and we need to generate the atoms in the flame. Let us just go to the interferences. There are generally 5 types of interferences generally observed in this. The spectral interferences. There are generally 5 important interferences. 1, spectral interferences. Spectral. 2, matrix interferences. 3, chemical interferences. 4, there is a chance of ionization interferences. Ions may also ionization interferences, and there may be a background background interferences. The spectral interferences can be eliminated by reading a particular spectra because the slides, few more slides are there. I'm just skipping and explaining you in a portrayal manner. Matrix interferences and chemical interferences, ionization also present, and background correction may be corrected by a Zeeman or background correction methods that are applicable. The spectral interferences can be checked out by avoided by reading particular overlapping spectrum of different wavelength. You can choose which is not interfering. This I said matrix interference. This is chemical interference, ionization interference. Which just needs much more discussion regarding this background interference. Now we are coming to the sample preparation analysis. Sample preparation. The weight 0.1 to 0.5 gram sample is taken. It is sometimes roasted or sometimes reconcentration techniques. Deconcentration is also applied from certain PGE and PEE. Platinum group elements. These are called platinum group elements, and rare REE. This is rare earth elements. Rare earth elements and platinum group elements can be analyzed by reconcentration techniques. The sample preparation is done by taking 0.1 to 0.5. It is roasted and hydrofluorized. Hydrofluorized, for example, most of the silicon dioxide should be hydrofluorized with hydrofluoric acid, SiF4 plus H2O. So this is volatile in nature. It is very important that silica is the main culprit of our analysis. We need to hydrofluorize the silica and remove it, and further analysis can be taken. So by oxidizing it in nitric acid and few acids also can be taken as per your choice of your method, and diluted to a particular concentration, and it is injected or it is passed to the nebulizer into the flame, and it gives atomization, and it can be calculated. Now coming to certain techniques, this is ranking of AS with the ICP-MS. This is an advanced technique. Inductively coupled plasma with mass spectroscopy. Nowadays, the sensitivity, when it comes to the sensitivity and accuracy and repeatability, this MSc, ICP-MS is also is generally used. But AS is not less than ICP-MS in high ranking method H. This is the methodology and support. The methodology and support, AS is the best suitable. It is having a good working range, and it is having relevant rate also. But when it comes to the methodology, when it comes to the sensitivity and working range, the ICP-MS is much more better than AS. But AS has also its own advantages, like interferences or spectral interferences, or it can be eliminated by having a single source. This is a single source. Okay, so with this, we'll conclude the atomic absorption spectroscopy, and we'll go to the next topic is UV visible spectrophotometers. Because simply, you might have known, we are having in Jabalpur laboratories equipped with this one. I hope now it is working or not, I don't know, but we are having this in our laboratory. This is a spectrophotometer, UV visible. This is a double beam. There is a measuring range of 190 to 100 nanometers, which is UV as well as a visible range. The photometric is a beam optics, a tungsten halo lamp and deuterium lamps is present. In this, deuterium lamp is present and tungsten lamp, two lamps are present. This is for UV range, and this is for a visible range. Generally, the source is taken. And monochromator is ternary turn spectrometer. Detector is silicon photoiodide and optimum temperature. Now you can see the source is allowed to pass onto this and to collimate it, pass to the optical system, and one of the parts to the reference, and one is passed through the sample. So that's why it is called double beam spectrophotometer. And the intensity of this is also Beer-Lambert's law, I0 by I, the decrease in intensity can be reduced, can be identified by the decrease in the intensity can be identified when it is passing through the sample. As this method is having a reference as well as sample, most of the interferences or what you call as interference can be eliminated. This is a Beer-Lambert's law where the concentration of lambda maximum as absorbance is generally measured along with the wavelength. This is the absorbance, maximum absorbance. Oh, this is that. It can be. It is a characteristic of particular element. What is the application? This for metals, salts. Application is generally this is applicable for metal salt solutions like titania and colored solutions also. We can analyze for any complexing materials also and colored compounds also. Where in normal volumetric methods we cannot just analyze this, and less than 1.4 ppm, 0 to 1.4 ppm, this can be easily analyzed. It is best suited for keto-analytic automatism and works on the Beer-Lambert's law. Advantages. I already talked about the advantages. The impurities, two beam of radiations are passed simultaneously. As the two beam of radiations are passed simultaneously to the blank and the sample, the voltage compensation is cancelled. And the impurities present in the solvent as well as the solution, as it is passed to the blank, it can be nullified. The accuracy of the beam is more than a single beam. This is Shimanju, you can just go through this. Now we have analyzed a very challenging task of this vanadium in graphite samples. Vanadium is forming a complex with it is measuring at 400 nanometers. The vanadium is estimated approximately by pounds and forms a yellow phosphotungstovvanadic acid. At 400 nanometers, it is measured by utilizing this sodium tungstenate. Sodium tungstenate is used along with phosphoric acid and it is in a sulfuric acid medium. Vanadium is analyzed. Why is the requirement of vanadium? Vanadium is very important material in alloys industry. High strength steels are generally made up of vanadium, and it is very important to analyze this vanadium in graphite samples. Generally in graphite samples we are analyzing. First is you are converting graphite into ash as the sample. After ashing the sample, you are going for a sodium carbonate fusion. Before going, you have to hydrofluorize the material. Hydrofluorize the material to remove silica. Remove the silica, and afterwards you go for a sodium carbonate fusion or peroxide fusion and extract it with water extract, and it is changed into complex. It is complexed with tungsten, sodium tungstenate, phosphoric acid, and presence of sulfuric acid medium. In this, you get at a 400 yellow complex is formed. Yellow complex is formed, which can be measured at 400 nanometers. Okay, this is the method. This is the principle and the methodology we have applied. You can just go through the literature of anything. We can analyze this vanadium. So in this method, I am talking about the instrumental method where we are utilizing the intensity, reduction of the intensity of the radiation, and the decrease in the intensity is the absorption of the particular concentration of the analyte. By that physical parameter, we are analyzing the quantity of the material. application, we very well know in the estimation of iron by 110 phenanthrene method is very quite evident that 110 phenanthrene can be analyzed by this method where you can just see this is a phenanthrene. Just having a nitrogen over here and nitrogen, and when it is when it is being reacting with iron, it forms a complex with 110 phenanthrene, the phenyl system, phenanthrene, 2 complex, which is and orange red in color. This complex is orange red in color, which can be measured 500 nanometers. Nanometers. The methodology is given here, and you can this method 1% ascorbic acid is utilized pH of 3.5 to 4, and along with it, a 20% of ascorbic sodium citrate. Citrate is very essential to maintain a pH of the same, and this is very important to maintain in this method. The pH is very important in order to analyze the iron, and you need to complex the material. This is the complex that is formed, need to analyze. This is the procedure, you just go through it, 110 phenanthrene. Now it is very important, we are going for an ammonical nitrogen. One of my friends is working in fisheries industries. He is a scientist in fisheries industries, and he's asked for the estimation of ammonical nitrogen. It is very important in maintaining of fish. Fish generally, they discharge waste products, nitrogenous waste products, waste of nitrogenous. Generally, in ammonium based. So the analysis of ammonical nitrogen, water and waste products, and this is application to the fisheries industries. The previous, I have talked regarding this iron, it is applicable to water systems which is less than 1.4 ppm. And in this method, we can analyze this ammonical nitrogen that is present in the water samples of the fish industries or hatcheries, or can be analyzed. But in this method, what you have done is very simple, and the ammonium content, you very well know about the Nessler's reagent. The ammonium content that is present will react with the Nessler's reagent. I can just give you an equation. K2HgI4, this is a Nessler's reagent. When it reacts with ammonium chloride, it forms in presence of gas. This produces iodide of millions base. That is mercury having 9 oxygen again, and an iodide. This is an iodide of millions base. Iodide of millions base. And along with it, you can get a this is the reaction. This is called iodide of millions base, which is yellow in color. This is yellow in color, and the complexes can be formed according to this method. You just go through the method. It is given in several literatures. Yellow complex is formed at a pH in this method. The pH is very important. You have to maintain at 10 pH, and at 410 nanometers. 410 nanometers, it is analyzed. So this is also an interesting method. We are running short of time. Let's just check out the very important aspects. I just want to interest. It is a direct DMA technique of mercury analysis, or a very wonderful technique for mercury. So, as a mercury which is present in the water, mercury generally, I just wanted to stop it, but I found it very interesting. This GMA 80, where it contains a method in which you can analyze just a minute. Generally, mercury is present in three forms. That is, elemental mercury, ionic mercury, and organic mercury. So this is much more dangerous than other. This elemental mercury is somewhat 1,000 times heavier than water. So this mercury is in form of two states. It is in elemental form, it may be Hg plus form, and it is also present in Hg plus 2 form. This is mercurous form, mercuric form, and metallic mercury. In this, a simple method is that mercury exists in a vapor phase and metallic state, atomic state. I mean to say, in the atomic state, the mercury can vaporize. It can vaporize. This is the concept that has been taken, that it can be directly vaporized and it can be converted. If it is present in this mercuric phase, it is converted, and mercurous phase, these are reduced, and it is converted into metallic phase by using certain reducing agent like stannous chloride. Stannous chloride is generally required for the reduction of this mercury, and the elemental mercury, whatever the vapors are coming, it can be directly analyzed. So you didn't have to, this is called as a direct mercury analysis. The analysis of this mercury can be done directly in a sample. It may be a soil sample, water sample, or any sample if it is contaminated with mercury. This is an instrument where it contains several boards in which directly the sample, this is a direct analysis. Why it is called as DMA? This is called DMA because direct mercury analysis. In this, they contain several boards in which the sample can be placed in any form. And this is allowed to pass into a converter which can, first it is being absorbed on this charcoal. First what happened? First you are sending the sample into the converter where the elemental mercury is vaporized and it is being absorbed on this charcoal. And after this charcoal, it is being converted, is placed into amalgamator. This is an amalgamator where the mercury will be amalgamated with certain gold interferences. It reacts with the gold and forms an amalgam. After the formation of amalgam, the mercury will be passed, the mercury vapors will be passed, and it is just get atomizes into elemental state, and it can be passed to this sample detectors. Here the temperature is maintained in such a way that the decrease in the intensity of the radiation is measured over here. It is measured over here, and it can be analyzed. You can just see, this is the boards, what I was just talking about, and you can place these boards here. That sample can be placed and it can be introduced. This can be introduced into this, where the temperature it is made and the mercury is allowed to pass through this. Only challenge is that how to drain the mercury into the channels. So here you need to convert this into certain inert atmospheric and atmospheric levels, inert levels. With this, I like to end this topic. I hope you found very interesting regarding this analysis of elemental mercury at last, but not least. And there is several industrial applications providing from food industry, fisheries industry, metallurgical industry, power industry, iron industry, several other industries where the applications are, the analytical chemists are challenging, where the environmental chemistry. My only answer to the solution of anything is, if any analyst will be analyzing the sample which of not a good job, I mean to say that if suppose any methodology, they want to analyze the sample, and after the generation of the results, they just don't care about the methods, but what are the pain we are going through is really appreciable, and you should have a thorough knowledge about the basic chemistry and the advanced features, and you have to abreast with the latest technologies that are going throughout the world. So with this, I would like to end my presentation, and I found very interesting that Sir Archimedes of Syracuse has said, "Give me a river long enough and a fulcrum on which to place it, and I shall move the world." So you are so confident enough, and you should have a confidence levels, the confidence intervals at lambda, at K alpha, that is at 98% interval levels. And Mr. Sir Isaac Newton has said that my powers are ordinary, only applications brings me success. So I'm very thankful to my gurus, my parents, and all the seniors who have taught me and shared me knowledge. I'm thankful to you. Thank you for your patient listening. Thank you.
We have time for one or two questions. Please, anyone who have any question, you can ask. So there is a question from Mr. Rahi. A sample whose all parameters are within formation limit, but value of COD is very high. What's its reason? So you can read it in the chat box.
Okay. Please write the question for yourself. The sample whose all parameters are within formation limit, but value of COD is very high. What's the reason? Other condition of XRD. Okay. And this question is I couldn't be able to get the sample whose all parameters are within permission. What sample and what are the parameters? And what value of COD is very high? Why is COD is very high? You should analyze why COD is very chemical oxygen demand. The contaminants are very much high. And what is the application, in which field you are analyzing that should be taken? For example, if you are analyzing in fisheries industry and the parameters like ammoniacal content is high, generally the COD levels also will be this. What type of, can I interact with her? Sample of all information limits, but the COD level is high. You have to check it out for other parameters, source. You have to go for advanced MS. Is there any elements which we are unable to analyze it? That is the main question.
Mr. Rahi, can you unmute yourself and ask your question? If you want, you can do that.
So what parameters you have analyzed, and is that analyzed quantity is totally sufficient enough to estimate that COD levels are high? What a sample? Is it fisheries or is it polluted levels, or underground water or surface water? What?
I think so he's talking about in general.
In general. No. I mean to say, 100% a chemist or an analyte cannot analyze 100 and 100.000. So he can analyze up to 99.9 accuracy. That too with several instrumental techniques. You need to check out what are the different possible methods. There's a heavy metals where you need to go for ICP-MS. Of course, it is on a trace quantity levels. But generally, have you gone for some other major elements like alumina or silica? Major elements. or you're talking about the COD levels, but it might be contaminated levels. So the question is not complete, I mean to say. Okay, next question is, what is the application of XRD? Am I right?
Yes, sir.
XRD. This is X-ray diffraction studies. X-ray fluorescence studies, we have discussed about the X-ray fluorescence studies where the composition percentage analysis is identified. Okay, in XRD studies, you will know the basic geometry of the crystals, where are the spacing and basic geometry of the crystals and empirical values. In XRD is X-ray diffraction studies, and you will know the spacing of lattice, where the actual crystals in the crystal lattice, where the atoms are placed. This is the study of XRD. Well, studying of XRD is a physical, but studying of XRF is a chemical composition where you can know the identity where ppm to percentage levels you are analyzing the chemical composition in XRF. But XRD is purely limited to the crystal structures. Am I right? Am I clear? This is your. Did you get your answers, sir? Hello. River water, BOD, DO, and parameters are with pollution limit. There is no industrial contamination. What is the so DC Rashi? The BOD and COD levels. Have you checked with the inter-laboratory comparisons? Have you checked up with the inter-laboratory comparisons or inter-laboratory comparisons? Hello.
Sir, I think he is talking like in general. He or she is a student.
Have been and you need to analyze in a careful manner, and you need to go for a total analysis of water. What are the contaminants, or you are talking in general, no? So there may be nitrogenous levels or some which are polluting. You are saying there is no pollution, but COD levels and you have to take for a inter-laboratory comparison test. Better. Okay. And
Any other questions?
any more questions? Any doubts?
I have one question, sir. You said there are two methods in X-ray diffraction to prepare a sample.
Excellent.
Yeah.
Excellent.
Pressed powder method and the glass bead method. Which one is better?
Okay, very good question. Wonderful. Glass bead method and powder press method. Powder press method is only utilized for when you're pressing the sample into a powder form, the X-rays are coming and hitting only on the surface of the material of a particular area. So you're analyzing a particular area and it will give scan results of a particular elemental composition of that compound. But in glass bead method, you are converting into a uniform sample. Here also, of course, you are grinding, you are making, you are binding, and you are making into a pellet. And in this glass bead method, you are grinding, you are making, and you are taking fluxes, and you are making a transparent glass beads where the interferences are reduced. And I do recommend this glass bead method is the best method than the powder technique. But powder technique is also applicable to few samples which are also best suitable. But I do go for a glass bead methods.
In the glass bead method, we are using directly the compound. We don't use any other compound for
We
making
are
the
using
glass.
our own compound, and along with the compound, you are trying to make into a soluble form. You are adding some fluxes.
Fluxes we are
The
adding.
fluxes may be, and if you run a blank sample, if you run a blank sample in absence of this sample, and you just compare the result, you get a wonderful result.
Okay, sir.
Am I clear?
Yes, sir. Yes, sir. Like in IR, we use two different methods. Like in IR spectroscopy, we can use KBR for making a pellet, or we can use directly the sample. If the sample is liquid, we can use directly that sample.
That is a crystal. You are making compressed pellet
Yeah.
to pass the radiation.
Yes.
That is, you are using the sodium bromide, or what you are using?
Potassium bromide. Potassium bromide.
Potassium bromide. What is your question then?
No, so I was comparing that with this only because this pressed powder method is similar to that of KBR. What we use in IR.
You are pressing the sample where the identity remains the same, and the sample should be
Yes.
sample should be and the homogeneity should not disturb.
Okay. Yes, sir. Thank you, sir. Now I would, is there any other question? Yeah, Priyanka Garwal. If we have some, you can read in the chat, sir.
Again, I have to go for the chat.
Okay, I will read it for you. If we have some metallic ore samples in high concrete, which is the best method? Concentration.
Okay.
In high concentration, which is the best method?
Okay. If you are having a metallic, if you have some metallic ore samples in high concentration ranges, for example, if you want to analyze a copper which is having around 20%, 20% or 30%, I already said in the first introduction that our forefathers is the best than our genes. My forefathers used to run like anything. They used to strongly build, but the generation where we are coming is becoming weaker. So I go for a wet chemical methods. For high concentration methods, if you are having a high concentration, the instrumental methods should be diluted and it should be amplified, and you can get the concentration where the concentration errors may also occur. So directly, if you are going for a wet chemical process, wet chemical methods, that is classical methods, this is the best for, I am a classical chemist. I always believe in classical chemistry because for a higher concentration and the repeatability and reproducibility of a high concentration samples are the best. And wet chemical techniques are the best. Classical chemicals are the classical methods are the best. Am I clear, Priyanka Agrawal? Hello. So you better go for a classical method, and you need to calibrate your standards. You need to calibrate your standards, and you are with a timely standardization of your primary and secondary standards is very important. Next, any more? Good interaction. I felt very happy.
I think, sir, because we are running out of time, we should move to our vote of thanks. I would like my colleague, Dr. Souvik Day, who is also a very important part of the organizing committee of this webinar. Please, Dr. Souvik Day, give vote of thanks.
Thank you, Dr. Chandni Pathak ma'am. Good afternoon all. As all good things comes to an end in life, so is this webinar. On behalf of the Department of Applied Chemistry, Jabalpur Engineering College, I take this opportunity to thank you, Dr. Chandni Pathak ma'am. So I am privileged to have this opportunity to give the vote of thanks. So good afternoon all, and as all good things in life comes to an end, so is this webinar. On behalf of the Department of Applied Chemistry, Jabalpur Engineering College, Jabalpur, I take this opportunity to propose the vote of thanks to those who are directly and indirectly contributed to this webinar organized by the Department of Applied Chemistry. At the outset, I thank our resource person, Dr. Nagabhushan Rao, for inspiring us today with his knowledge and experience. We are thankful to our Honorable Principal, Professor A.K. Sharma, and Head of the Department, Applied Chemistry, Honorable Professor S.K. Srivastav, for their motivation and enthusiastic support. I would like to extend my gratitude to the coordinator of the event, Dr. Chandni Pathak, without whom this webinar would have been impossible. A special thanks to the organizing committee, Dr. Rajiv Chandak, TCUB coordinator, Dr. Sailaja Shukla, TCUB nodal officer, Dr. Anubha Maheshwari, Dr. Silpa Saxena, and Dr. Kanchan Khare, as well as Dr. Vasudha Saxena and Dr. Pratap Reddy for their unflinching support and coordination. Our heartfelt thanks to all the participants for their active participation. With these warm words and a kind message, we move to the end of today's webinar. Thank you all. Thank you all again. Stay safe. Thank you.
Just a minute. Just a minute. Just a minute. I just want to thank my professor, Sri S.K. Srivastav sir, Principal, Civil Engineering College, and Coordinator, Dr. Chandni Pathak, and Convener, Dr. Vasudha Saxena, and all the organizing committee. Very important for this to happen. Thank you. Thank you very much.
Thank you, sir.
Thank you everyone for joining us today. Please everyone fill the feedback form. I have shared the link in the chat box to get the certificate for today's webinar.